Hi everyone, how are you doing? Hello Raj, hi Sonam, hello Samir, hi Arjun, hello Rakesh. So let's get started. Today we are going to see a new topic which is similar matrices and then followed by diagonalization. Okay, this is a small topic, but it is very much necessary also. So let's just see. Okay, it is interesting at the same time. So let's just see what is a similar matrices. So let's suppose that we have two matrices A and B. A and B are two matrices said to be similar if they satisfy this kind of relationship, which means B equal to S inverse AS or vice versa, or A equal to S inverse BS, which means we will say that if if there is a matrix S exist such that B and S share such kind of relationship, then we say that these two matrices are similar matrices. Similar matrices represent the same linear transformation but in the different bases. Okay. For example, let's suppose A is a matrix of or you can say standard matrix of a linear transformation. Okay. A is a standard matrix. Sorry, A is a standard matrix of a linear transformation. And let's suppose that there is a matrix M that I want to calculate, which is also the matrix of linear transformation. But here the input basis, okay, input basis is let's suppose U, and the output basis is let's suppose V. Then what will the M? Can anyone tell me quickly? What will the M? Just let me know. Okay. So the M will be V inverse AU, right? If you recall from the last lecture. So basically, I can say that M and A, okay, M and A are similar if if input and output basis is same. For example, if let's suppose input and output basis is same, okay, let's suppose this is also U, okay, suppose this is also U, then in that case, what you will be writing? This will be U inverse and this is V. Sorry, this is U. So basically I can say M equal to U inverse AU if input and output basis is same, right? Or you can say that it is with respect to the basis U. Then we say M M and A are similar. M and A are similar matrices. Is this fine to everyone? Let me know. Okay. I mean, this is just from the last lecture. So this is a definition of similar matrices, that if there is a, okay, like how to find that matrix and these things are different story. But let's suppose if there is a matrix such that it satisfy S inverse AS is B, then we say it is a like A and B are the similar matrices. Okay. So this is the definition of similar matrices. And in the conceptual sense or in the theoretical sense, you can say they represent the same linear transformation related to different bases. Okay, the same linear transformation related to different bases. By the way, have you attempted the quiz that I have uploaded? How many of you have attempted the quiz? Let me know. The quiz that I uploaded. So there was a quiz. This quiz I have uploaded already. So just attempt this quiz as soon as possible, right? Just attempt this quiz. And whenever you see any particular question which is interesting to you, then just upvote that question. And if you see that there is someone has put the answer and that answer is little interesting even, then just upvote that answer. It just motivate us also to put good questions. See, for every quiz we just see that okay, okay, let's suppose out of 16 questions, let's suppose 15 question has gotten or maybe 5 question has gotten good upvotes, then it motivate us to put better questions in the next question. Anyway, we will be putting the better question. But just like you, we also need the motivation. I mean, just like you, you might be needing the motivation for the for your studying. Similarly, we also need the motivation for the teaching. So that's why I'm just saying that just upvote whenever you find that okay, this question is good, this answer is good. Okay, just upvote. Great. So if we say that A and B are the similar matrices, then we represent then matrices like this. Okay, A and B are the similar matrices. I mean, this is just a symbol. Okay, A and B are the similar matrices. Or equivalently, you can say there is a matrix P such that A equal to PB P inverse or AP equal to PB. Okay, you can write like this also. Why? Because because if A equal to PB P inverse, or maybe it doesn't really matter. You write like this or you write like this. See, you write like this. Okay, it doesn't really matter. Why? Because here maybe okay. For example, here let's just suppose it is some Q. Okay, doesn't really matter how you're writing. Which means you can just take P inverse as Q. If you take P inverse as Q, you can write like this, right? So it doesn't really matter you're writing inverse first or you're writing inverse later. Okay, it doesn't really matter. So what I'm saying is that if you have something like this, you multiply by P both side, you can get AP equal to PB. Okay, AP equal to PB. So if that is the case, then we say that A and B are the similar matrices. Okay. Okay. So just tell me, is this true that A is similar to itself? Can you write? Okay, just tell me, can you write A equal to some matrix, okay, into A and the same matrix inverse? For example, P. Okay. Can you tell me what is the value of P such that this relation is satisfied? Yes. So if you take P equal to identity matrix, then this relation is satisfied, right? So this is true or false? Tell me. The first one is true, right? This is true because take 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 P is equal to identity matrix, right? Here I is identity matrix. I hope that is fine to everyone. Okay. Now tell me if A is similar to B, can I say B is also similar to A? What do you think? So when we say similar, we say A is similar to B means A equal to some matrix B and the same matrix inverse, right? Can I write B also similar in the similar fashion? Let's just check. This will be AP, I think, right? AP equal to B. You multiply by P both sides, it will be PB. And then can you write P equal to sorry B equal to you multiply P inverse like this. Yes, that is there, right? So basically, you can write some matrix into A into that same matrix inverse. So basically, if A is this, then B is this, right? Does it really matter that you are writing inverse first and these things? Doesn't really matter. I never said that okay, you have to have some inverse. See, it is just a convention, which means this matrix, if this is P, then P inverse must be here. Inverse of this, these two matrices are inverse of each other. Okay, so A and B are similar to each other. If you can write A equal to B, any matrix here, okay, P inverse doesn't really matter, but these two matrices are inverse of each other. Similarly, similarly, you can say B is similar to A if you can write something like this. So basically, if A is similar to A, I mean, if A is similar to B, then B is also similar to A. Okay. So this is also you can say true, right? Because if that is the case, then this is the case. If A is similar to B and B is similar to C, then A is similar to C. What do you think? See, A is similar to B and B is similar to C. Then can you say A is similar to C? Let's just check it. A similar to B means A equal to some matrix B, the same matrix inverse, B equal to some matrix, and then C, same matrix inverse. Okay. Now let's just, I mean, this is given to you. From this, can you say that, okay, can you eliminate this b? So from this, can you write it like this? A equal to p into p into, instead of this b, can you just put the whole value, which is q c q inverse, isn't it? Let me know, right? Isn't it same as saying a equal to some matrix, maybe it is pq c, and then pq inverse, the same matrix inverse. So you can say like this, right? So that's why A is also similar to C. If A and B are similar, B and C are similar, so it follows transitivity. Okay. Although it is not important to know, but how many of you know about equivalence relation? Equivalence relation, reflexivity, and what we call it, symmetricity and transitivity, right? I mean, it is not important to know, but that's fine. So this A and the similar matrices actually follow equivalence relation. So this is reflection, I mean reflexivity. This is symmetricity. This is transitivity, right? So they follow equivalence relation. Anyway, if you don't know, it is not important to us, but I'm just asking if anyone knows about the equivalence relation. So similar matrices follow the equivalence relation, right? Okay, cool. Now, let's just see this particular theorem, or let's just try to prove. Okay, let's just try to prove what they are saying. So they are saying is that, suppose A and B are the similar matrices, then A and B have same characteristic polynomial and hence the same eigenvalues. So what they are saying, if A and B are the similar matrices, then they both follow the same characteristic polynomial. So what is the characteristic polynomial? You can write the characteristic polynomial for A like this, right? And the characteristic polynomial for B will be something like this, right? I mean, they are saying that they are having the same characteristic polynomial, which means the lambda is same. Okay, in both the cases, the lambda is same. So let's just see if we can prove it. So let's suppose that, okay, A and B are the similar matrices. Let's suppose this is the case, right? Now, now let okay, let's suppose this b minus lambda I, if I want to find out the characteristic polynomial of b minus lambda I. So instead of b, you can put p inverse ap, okay, and then minus lambda into, instead of I have put p inverse p, okay. So you can take p inverse common and p common from here, and then if you try to find out the determinant of this, so maybe I can just go to the next page and try to tell you. See what I'm trying to say. If you try to find out b minus lambda I, find out what is this b minus lambda I. Okay, what it will look like. This b, since a and b are similar, that's why b is nothing but p inverse ap, isn't it? Is this okay to everyone? So this is p inverse ap minus lambda I, right? Which is same as p inverse ap minus, instead of I, can I write p inverse p? Okay. Now this is lambda. Is this a scalar or is this a vector? Tell me. This is a scalar, right? Since this is a scalar, that is why you can write it here, or maybe you can write it here, or maybe you can write it here. Okay. So you can write this anywhere since this is a scalar. So that's why this is P inverse AP minus, I'm just writing it in between. Okay. Okay. I'm just writing it in between. Now you can take P inverse common. Sorry. This is lambda P. You can take P inverse common. And then again you can take P common, right? Now, from here, you got to know that b minus lambda I looks like this. Okay, b minus lambda I looks like this. Now, can you tell me if you take the determinant of b minus lambda I, how it will look like? determinant of b minus lambda I. Can I say it is same as determinant of this whole thing? Right? It is same as determinant of this whole thing. Okay. Is this fine to everyone? Can I say it is same as 1 by determinant of p into determinant of a minus lambda I into determinant of p? Let me know. Is this fine to everyone? So from here, can I say it is same as determinant of a minus lambda I? Right? So basically, whatever the lambda which satisfy this determinant to be zero, okay, for I mean both are actually same, okay. So both characteristics of polynomial are actually same. So it means eigenvalues are same, okay. Which means for lambda equal to one, let's suppose for lambda equal to one, this determinant is zero. Then tell me for lambda equal to one, this determinant will be what? Zero, right? I mean, this is basically whenever you are putting some lambda, if you put lambda one here, you will automatically put lambda equal to one here. If this is zero, then this is also zero. So basically, the eigenvalues are same for the similar matrices. Okay. So just remember this. You do not need to prove it again and again. Okay. Just remember this, that just a second, that eigenvalues are same for similar matrices. Got it? Okay. And since the eigenvalues are same, that is why the determinant is also same. Okay, so let's just see this question. Tell me whether this is true. I mean, how many of it are true or how many for the false. Okay, so let's just have it a question as true false. Tell me, is this true? If the eigenvalues are same, then the determinant is same. Tell me, this is true or false? Do you remember the relationship between the eigenvalues and the determinant? Yes, right. Determinant is nothing but product of eigenvalues. Right, right. Okay. So this is true. I can say this is true, right? This is true. And the reason is the determinant is equal to product of eigenvalues. A is invertible if and only if B is invertible. What do you think? This is also true. Why? Because if lambda equal to 0 is an eigenvalue of any one of them, okay, then it is automatically of other one. If lambda equal to 0 is not eigenvalue, then it is not of any other one. So if this is invertible, matlab lambda equal to 0 is not eigenvalue, then obviously this is invertible, right? Because eigenvalues are same. So that's why this is true. This is also true. Now you tell me this. A and B have the same rank. Okay, C I will do, but you first tell me this. This is true or false? This is also true, obviously. We just saw it, right? And what about this? This is also true, right? This is also true. Okay. They have the same rank. Is this true or false? What do you think? No, same eigenvalue is okay, but same rank. How we can, be sure about it that they have the same rank? Okay. We can try proving it that the similar matrices have the same rank. So do you want to try this, formally as an homework, that why similar matrices have the same rank? Ajay is saying rank is number of non-zero eigenvalues. No, if lambda is equal to not zero, okay, for all lambda, then rank is n. Rank is n. If that is the case, if lambda equal to zero, okay, which means if lambda is equal to zero, then rank is just less than n. Okay, you can't say that how much. I mean, you can't just say that okay, rank is n minus one, n minus two. So here we can't say anything. Okay. Yes, rank depends on the dimensionality of null space. That is fine, but that's the point. That okay, the rank is same or the dimensionality of the null space is same. How to prove it? So let's just try to prove it. Maybe suppose X is in the null space of A, which means if AX equal to zero, then can I say that there is some vector, okay, if AX equal to zero and A and B are related like this, right? A equal to, let's suppose, PB, P inverse. So so it is basically as good as saying, or maybe you can say AP equal to PB, right? Or from here, maybe you can say if AX equal to zero, then PB inverse into X equal to zero. Or maybe let me write P inverse first. Doesn't really matter, okay? Just in convention. Let me write P inverse first. So here it will be like this, right? And from here, can we say BPX? You multiply P both side, BPX equal to 0. So if X equal to, I mean, AX equal to 0, X is in the null space of A, then from here, what we can say? Then we can say PX is in the null space of B. Is this okay? I mean, if X is in the null space of A, then PX is in the null space of B. Is this fine to everyone? Okay. So suppose that X is in the null space of A. Then we have just seen that there is some vector Px that is in the null space of B, right? Now, suppose in this null space there are, let's suppose, only three linearly independent vectors, right? Which means dimensionality of null space of A, let's suppose this is 3, which means only x1, x2, x3 are linearly independent. Okay, let's assume this. Then you tell me about px1, px2, px3. Are they also linearly independent? Do you remember we have proved that okay, if x or maybe v1, v2, v3 to vn are linearly independent, then transformation of them, linear transformation, will also be linearly independent. Do you remember there was one question we did it? How many of you remember that if they're linearly independent, then that linear transformation is also linearly independent? We did at least some kind of question we did in the previous class, right? Okay. So what I'm trying to say here is that if X is in the null space of A, then there is some vector Px is also in the null space of B. Which means if you have three linearly independent vector which is in the null space of A, then at least three तो यहाँ पे होंगे ही होंगे. मतलब I have just proven one thing, is that dimensionality of null space of B is greater than equal to dimensionality of null space of A. Is this fine to everyone? No transformation. This there is no guarantee of P. Okay, it could be anything. P could be any matrix. If x1, x2, x3 are linearly independent, then px1, px2, px3 are linearly independent. So if you have three vectors here in the null space, then you definitely have the corresponding three vectors, right? Maybe कोई यहाँ पे x4 या फिर कोई b4 or there might be some other vectors in this null space, but at least these three are there which are linearly independent. Is this fine to everyone? Okay. So let me just revise. See what I'm trying to say. कि अगर let's just do step by step. Okay. Let x is in null space of A. What does this mean? It means it means that ax equal to 0, and we already know that A and B are the similar matrices, so that's why this relationship is there. So I'm just substituting this A as P inverse BP, right? I'm just substituting this A as P inverse BP into x equal to 0. From here you can say BPx equal to 0. So from here we got to know if x is in the null space of A, then 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 the corresponding some vector px is in the null space of B. Is this okay to everyone? Tell me. Right? Similarly, I mean, since they're similar matrices basically, so you can flip them, which means you can assume there is any vector, let's suppose for B, which is in the null space of, let's suppose, B, then can't you just say that for some matrix, okay, let's suppose QB is in the null space of A. I mean, यहाँ पे कोई null space में होगा, तो उसके corresponding there will be some vector in the null space of A. See, if there is a vector x in the null space of A, so corresponding, okay, px is in the null space of B. Similarly, I just need to flip, okay, instead of A, I just need to write B. Instead of A, I just need to write B. Instead of B, I just need to write A. Instead of B, I just need to write A, right? So it will be px equal to null space of A. So I can just flip A and B, okay? This is, you can say, due to symmetricity, doesn't really matter. So if I'm taking a vector here, then the corresponding vector is in the null space of B. Similarly, a vector here, if I'm taking the corresponding vector in the null space of A, which means, which means these vectors I already know are linearly independent if x are linearly independent, right? So अगर यहाँ पे तीन वेक्टर हैं, तो यहाँ पे एटलीस्ट तीन तो हैं, और यहाँ पे हर एक वेक्टर के लिए यहाँ पे भी एक वेक्टर है. So what I mean to say that for this particular, I mean, out of this particular thing, I can say the dimensionality of A, null space of A, is basically lesser than equal to dimensionality of null space of B. And from here, I will prove the otherwise, which means I will prove that from here, dimensionality of null space of B is lesser than equal to dimensionality of null space of A. From both of this, you can prove that actually the dimensionality of null space of A and B are same. Okay. So from both of this, you can prove that dimensionality of null space of A and null space of B are same. Okay. So which means the nullity is same and which means the rank is same. So this is just one proof. I think Saurabh Sahu has given some other proof. Let's just see. So he's saying A, B, and B have the same non-zero eigenvalues, right? Using this, we can say rank of AP. No, this I don't think this is 100% solid proof. Rank is not the number of non-zero eigenvalues. Okay, rank is not number of non-zero eigenvalues or something. Okay. Okay. So this is just one way of proving it. But there could be definitely some other ways. So let's just do one thing. Let's just take it as an homework. Okay, take it as an homework to prove that both share the nullity or the rank. Okay, we have proved for nullity, and then eventually they will share the rank. Okay, I mean both have the same rank. Okay, you can just try proving it, and then we can discuss in the next lecture also if there are some other proofs available. But today I just proved it, whatever came to my mind. Okay. I mean, this is one proof I saw some time back. So I just proved it because it got, I just got to recall this kind of proof. But we can see if there are some other interesting proofs also. Okay. But yeah, these all properties are very, trivial kind of properties which you should know that, okay, eigenvalues are same, determinant is same, rank is same, nullity is same, like this. Okay. And because they are similar matrices. A lot of things are shared. And that's why they are called similar matrices. Okay. What are the things that they share? If A and B are similar, then what are the things they share? Rank is same, eigenvalues are same. These are the two main things they share. Okay. I mean, determinant and these things are just, byproduct because eigenvalues are same. Then obviously the determinant will be same, right? So determinant will obviously same. Invertible, these things are same. So these are the two main things that rank and eigenvalues are shared. Okay. See, rank similar, then they have the same determinant, they have the same trace, rank, nullity, and these things, right? So rank and eigenvalue of the similar matrices are same. Can you just remember this? This is quite important. Okay. Okay. Now let's just see this question. Find a matrix S so that shows that A and D are A similar to this D, which means we need to find some matrix S which is something like this. Okay. Or in other words, you can say AS equal to SD. Okay. So find some matrix S such that AS and SD are same. This is the question. Would you like to try for 1 minute? Just try it. Okay. Just try and let me know if you are able to find. So maybe I can just give you a hint, a little hint, which is that you can assume S to be ABCD. Okay. And then A, which is minus 49 into 80 into minus 30 into 49 into S. Okay. Which is ABCD equal to ABCD and then multiplied by D. What is that D? D is, I think, easier one, minus 1, 0, 0, 1. Okay. Just try it out. So if you are thinking, like it will be a lengthy procedure, then yes, it will be. So basically, it will be a lengthy procedure only. So you will be having, multiple equations. Let's suppose four equations, something like this, and then you need to solve it. Okay. So, for example, you can, take these four equations and make it. I think they have made it just like this: A into C equal to um. Okay, this is 48, 80, 30, 49. I think this is 49 or something like that. So basically, you need to solve it. Okay. There is no other way. Anyway, this is out of our interest. They won't be asking this, but by chance they ask, okay, that what is the matrix that satisfy such that these two matrices are similar. Then this is the only way. Okay. Okay, so we will see. Okay, we will see some, some other method, if that is the case. Okay, we will see some other method if we can find some other method such that we can, find out this s. Okay, we will see that if this matrix A is similar to some diagonal matrix, then there are easier methods actually. Okay, if this matrix A is similar to some diagonal matrix, then there are easier methods. So we will see that also. Okay, but before that, let's just see if you can solve this question. Are these two matrices similar? What do you think? Are these two matrices similar? Okay, some people are saying no, right? Can you tell me why? Because trace must be same, right? Trace is nothing but, you can say trace determinant, and trace is the summation of the eigenvalues. This is 5, this is 7. So trace is different. So I can say no, because because trace trace of A is not equal to trace of B. So actually checking whether this is similar or not, it is, I mean, if it is not similar, then it is very, very easy. Okay. If it is not similar, then this is very, very easy. You can just check using trace, or using the determinant or something like this, right? A is not similar to B. Okay. Let's just see this. Similar matrices have the same eigenvectors also. They have the same eigenvalues, but what about the eigenvectors? So for example, let's suppose A is similar to B, which means A equal to P, B P inverse, right? Let's suppose X is eigenvector of A. So here AX equal to lambda X, right? Okay. Then can you find out? Let me multiply by P. uh, Okay, let's just write it like this. Doesn't really matter, but I'm writing P inverse first. So P is nothing but BP. Okay. Then if you multiply by X both side, then it will be PAX equal to BPX. Okay. AX is lambda into X. So it will be P lambda X equal to BPX. So B into some eigenvector, I mean some vector equal to, you found out that okay, B into Px is coming out to be lambda into the same vector. So it means lambda is the eigenvalue, that is fine, but Px seems to be the eigenvector, right? Px seems to be the eigenvector, not X. Are you getting what I'm trying to say? Okay. So let's just do one thing. You don't look at this slide, okay? You don't look at this slide. Just try to see that if Ax equal to lambda x is given to you, and uh, then the other thing is that A and B are the similar to each other, which means you choose to write in whatever way who you want to write. So basically, I mean, you want to write inverse here or you don't want to write inverse here. It is up to you. But these two equations are given to you. Try to see that okay, B into some vector that we know that lambda into the same vector will be here. But what is that vector? Okay, will it be x p square x ax, or what is that vector? Okay, just see and just let me know how many of you are done with this calculation. Okay, just try to do it. No, do it by your own. Okay, so how many of you are done? It's easy calculation, I think. So maybe I can just tell you. See, if A equal to P inverse, then I think we did it here, right? So yeah, I'm writing in this way. Then P equal to BP, and then I'm multiplying by X. Then I got to know that okay, B into PX is lambda into PX. So basically this is true or false? Tell me. This is for the eigenvectors. This is false. Okay. Yes. Three independent eigenvectors, and A is similar to. Okay, I will come to this. Okay, A is similar to diagonal matrix, and I will come to this. Maybe you will not get to understand quickly. Okay. So by the way, are you understanding this similar matrices little bit? Okay, most probably, right? So tell me, are these matrices, are these matrices similar? Are these matrices similar? Then answer is no, right? Okay. You can check the rank, you can check the trace, or you can check whatever you like to check, right? So if it is a counter example, it is very easy to check. Now you know what is a diagonal matrix, right? How many of you know what is a diagonal matrix? There's a apart from the diagonal, all the elements are zero. That's called diagonal matrix, right? Is this a diagonal matrix? Is this a diagonal matrix? Yes, right? Okay. Tell me, is this a diagonal matrix? Suppose instead of three, I just have zero here. Is this a diagonal matrix? Yes, right? Okay. What about this? Is this a diagonal matrix? I have zero at both the places. Yes, right? Okay. Just a last one. What about this? Zero. Basically, zero at the diagonal. What do you think? Diagonal, if it's only non-zero entries, and I mean non-zero entries can be on the diagonal, okay? If only non-zero entries are on the diagonal, which means that apart from the diagonal, okay, k1, k2, k3 could be anything, but apart from the diagonal, it should be zero. And basically, the interpretation of this that apart from the diagonal, it should be zero. What is on the diagonal, whether it is zero or non-zero, doesn't say anything. So this is diagonal, this is diagonal, this is diagonal, okay? Okay, this is diagonal. So all are diagonal, okay? No, there is no need to no need to have at least one non-zero or something like this, right? There no need to have at least one non-zero. So all are diagonal matrices. Okay. Now let's just see very interesting topic which says that can we find a diagonal matrix D that is similar to A? See, you know that A and B are similar if some kind of relationship exists, right? Then we say that A and B are similar. A and B are similar to each other, right? Okay. Now this is right. Now they're more interested in something else. They are saying that not just a random matrix I want the similarity, I want the similarity with the diagonal matrix. Okay, so they are saying that what we want is that we want A to be similar to some A to be similar to some diagonal matrix. This is their requirement. Okay. Now let's just see, can we find a diagonal matrix D that is similar to A? Okay. So this is what we want to check. Can we find a diagonal matrix D that is similar to A? Is this fine? That what we ultimately want to do. So basically, we know that two matrices are similar to each other if this exists, right? But now they're a little more greedy. They are saying that okay, basically we don't want just any random B. We want to see whether it is diagonal to, I mean, it is similar to some diagonal matrix, okay, D, where D is a diagonal matrix. This is what we want to check. Okay. So let's just see. Let's just see if we can check it. So, for example, let's just take some matrix A. Okay. Let's just take some matrix A and let's just do one thing. Let's just find out the eigenvalues of this matrix A. Suppose these are the two eigenvalues and these are the two corresponding eigenvectors. Okay. These are the two eigenvalues and these are the two corresponding eigenvectors. Then tell me what will be A into V1? Won't it be lambda 1 into V1? Tell me, is this true to no, is this true or false? This is definitely true, right? What is A into V2? This will be lambda 2 into V2. Okay. So I mean individually we have seen them. I go, okay, A into V1, A into V2 like this. Which means that A, this is if this is A, okay, if this is A, then then we know that A into V1 equal to lambda 1 into V1. A into V1 equal to lambda 1 into V1, right? A into V2, A into V2, sorry. A into V1 equal to lambda 1 is 3 into V1. A into V2 is lambda 2 into V2. We have seen this as a, different equations. Can we just combine them? I want to show you something. Can we just combine them? Yes, most probably. So we can write it like this. A, which is 1, 2, 2, 1. And then both the eigenvectors. Just try to write both the eigenvectors, which is 1, 1 and minus 1 and 1. So what it will be? Can anyone tell me? What is the first vector here? It will be, can anyone tell me directly? 3, 3, right? And the second vector minus 1, 1. See, see how I'm doing it. I told, I think in one of the lecture also. If you multiply this A with, let's suppose, I mean, I'm not opening up this A, okay? I'm not writing this A as a square thing or something. I'm just writing it just as A. If you're multiplying, let's suppose B1, V2. It is same as, I think in change of basis matrix also I told it, okay, in linear transformation also, it is same as AB1 and AB2. Is this fine to everyone? Why that is the case? क्योंकि this, okay, see, as you know that AB1, how do you multiply A and B1? It is like that all the linear combination of columns of A you will be writing, right? So here also, if you multiply two matrices, right, A into this will be linear combination of columns of A and the coefficients will be coming from B1. So basically, A into something like this is like this only, right? It is fine to everyone that how we can see two matrix multiplication like this. If there are two matrices like this, then we can just see like this. Okay, tell me, is this okay? Okay. Now suppose V1 and V2 are the eigenvectors. Okay, on top of that, it is the eigenvectors. Then what you can say? It is lambda 1 V1, lambda 2 V2. Is this fine to everyone? It is lambda 1 V1 and lambda 2 V2. Let me know if these are the eigenvectors. I'm just telling you, okay, what I'm doing here, that I'm just writing one matrix A. I'm writing their eigenvectors here. I'm multiplying. Okay, let's just forget everything. I'm multiplying a matrix and a matrix of its eigenvectors. Then it will look like this. Then interestingly, okay, interestingly, This is little interesting and tricky also. This is same as lambda 1 times this vector. This how you got this vector? Lambda 1 times this vector, and how many times this vector? How many times this vector you have taken to get it? Tell me. Lambda 1 times this, and how many times of this? 0, right? 0 times of this. Similarly, 0 times of this and lambda 2 times of this. Okay? Or if you can't go from here to here, just try to see if you can multiply these two and you can get it. Okay? From here to here, at least you should be going. Okay? Is this direction fine? From here to here, you should be able to understand that this A into matrix of eigenvectors is nothing but ultimately it is the eigenvectors into the matrix of eigenvalues. Let's just call this matrix of eigenvalues as capital lambda. Okay. So let's just call this as capital V. So basically what I'm getting here is that A into capital V equal to capital V into capital lambda, where capital V is a matrix of, tell me, matrix of eigenvectors, right? If you multiply any matrix with its eigenvector, doesn't really matter what kind of matrix it is, right? You multiply any matrix with the matrix of its eigenvector, then see, earlier we used to write Ax equal to lambda x, right? In individual terms, we used to write Ax equal to lambda x. Can I write it like this? X equal to x lambda. Will it be wrong, or it will be okay? It is okay, right? I mean, Ax equal to lambda x, Ax equal to x lambda doesn't really matter. So earlier we were just having one vectors, right? Ax equal to x lambda like this. Now I'm just saying you have all the vectors here, all the eigenvectors here. AV, okay, V is all the eigenvectors, a matrix of all the eigenvectors equal to, earlier it was x lambda, now it is V lambda. Lambda is a diagonal matrix here, right? Diagonal matrix of eigenvalues. Okay. So let's just see that what I'm trying to say. I'm just asking you, okay, I'm not asking you too hard. I'm just asking you to just multiply two matrices, A into its own eigenvectors, V1, V2. Can you people try to do it again by yourself? Just tell me. Okay. If you want, you can, speak up. I mean, open up your mic. You can just unmute yourself and just let me know. Is this okay? Anyone wants to do it with me? यहाँ तक कोई दिक्कत? Fine, right? Okay. Is this also fine? Tell me. Okay. Now, just a last thing, which is little tricky. This way it is tricky, but other way it is easy only. It is just that I want to write B1, V2 separately, and this is multiplication of diagonal matrix. Just check lambda 1 into this vector plus 0 into this vector. Won't you be getting this vector? Right? So this is same as this. Now, this is same as V into lambda, and let's just call it A into B. Okay. Earlier, what it was? Ax equal to lambda x, or let me write it. I mean, we used to write it like this, or let me write it x lambda. Earlier, it is, if it is just one vector, then x lambda. If it is all the eigenvectors, then V into capital lambda. Capital lambda is a diagonal matrix. Tell me, for this to happen, have I assumed anything that A should be invertible, A should be symmetric, A should be flan, A should be decan? Have I assumed anything? Or this is true for any matrix? Just let me know. Or the eigenvectors should be independent, eigenvalues should be different, or anything. Have I assumed anything? I don't think I have made any sort of assumption, right? So this is even true for any matrix. Okay, any square matrix, this is true. Okay. Now see, now let's just see. See, I was at here. Now basically, if you multiply in that term, Okay, if you multiply the matrix A with the whole B, then ultimately you will multiply. Ultimately you will be getting, okay, you can separate this V out, and this is the capital lambda, right? And this is true for all the matrices. So let's just see step by step. See, this is also called as eigenvalue decomposition or diagonalization. Let's just see it step by step. So let's suppose these are the eigenvectors. Okay, let's suppose these are the eigenvectors that I have here, which is u1 to un. Let's suppose these are the eigenvalues. Let's just consider a matrix U, which is a like columns of U are the eigenvectors. Okay, something like this. Till now, this fine to everyone. इसको फिर we can write like this, and then we can write like this. Okay. So in this process, there was no assumption, right? So finally, we have this for all the square matrices. Okay. Now assume, okay, let's just now have the first assumption here. Assume U inverse exists. What is a U? Can anyone tell me what is U here? What is a U? Anyone? Yes, use a matrix of eigenvectors, right? Yes, Tejas. That is correct. That use a matrix of eigenvectors. So if we use a matrix of eigenvector, and now I'm saying let's just assume that U inverse exists. What does this mean actually? Eigenvectors are linearly dependent, independent. Linearly independent. Yes. So it means okay, this is my first assumption. If that happens, okay, if that happens, then if U inverse exists, then I can write like this, right? Then A equal to this. So for any matrix A, if if the eigenvectors are linearly independent, then this happens. Is this okay? Now tell me whether this is true or false. Okay, that A is similar to a diagonal matrix if all eigenvectors, this is true or false. Just think about it. A is similar to a diagonal matrix. Okay, see, this lambda, the capital lambda that I have written here is actually the diagonal matrix, right? Diagonal matrix of all eigenvalues. It is similar to diagonal matrix if all the eigenvectors of A are linearly independent. This is true, right? This is true. Okay, great. Now let me know, is this understood to everyone? Is this understood? Okay. So basically, if U inverse exists, then we have something like this, or you can write it in this way also, right? Since both are similar, then you can write it in this way also. A and the diagonal matrix lambda are similar. So either you write it like this, okay, or you write like this, doesn't really matter. This is called diagonalization. Diagonalization means that you multiply A with something, then ultimately the result is diagonal matrix. Okay. So under what condition U inverse exists, by the way? These are the conditions. If columns of A are linearly independent, that is A has n linearly independent eigenvectors, that is A has n distinct eigenvalues. What if A doesn't have distinct eigenvalues? Can U inverse exist? Tell me. Then also, columns, then also eigenvectors could be linearly independent, right? We have seen this. Do you remember this? How many of you remember? That if the eigenvalues are different, then definitely eigenvectors are linearly independent. But if they're same, then also the eigenvalues could be linearly independent, right? So maybe it is not very good line to write it in our context. So let's just remove it. I mean, it is not necessary to have and different eigenvalues. They could be same also. I mean, the eigenvalues could be shared also. We just want and linearly independent eigenvectors. So basically, A is diagonalizable, okay, or A is similar to diagonal matrix, or in other words, A is diagonalizable if and only if and only if we have a dimension of A, I'm assuming n cross n, okay? We have n linearly independent eigenvectors of A. Let me know if that is understood to everyone. We can diagonalize, or you say it is similar to diagonal matrix. I mean, both are the same words. If and only if you have n linearly independent eigenvectors, okay, of A. Suppose A is symmetric, then situation is even more convenient. Do you remember for the symmetric matrix, the eigenvectors are always linearly independent? Do you remember this? Do you remember? For the symmetric matrix, eigenvectors are always even orthogonal. Okay, eigenvectors are always orthogonal. So So in the symmetric matrix, basically eigenvectors are always orthogonal, or you can say, let's just assume that we normalize them also. Normalize means like we can divide it with their norm. I mean with their length of the eigenvector. Then it will be normalized. So let's just compute this Q, and then if this is normalized sense, then basically Q U transpose U will be identity matrix if this is normalized, right? Something like this. So you can say if U transpose U is identity, then U and U transpose are inverse of each other. Which means earlier, if we had to write this U inverse, then we can replace this U inverse by U transpose. Only if this A is a symmetric matrix. So what I'm trying to say here is that if A is a symmetric matrix, then situation is even more convenient. The reason is that eigenvectors are orthogonal, and if we make it, just like I mean, it is just a division of some norm. So if we make them orthonormal, okay, if we just normalize that, then then ultimately what you can do, instead of writing U transpose, sorry, U inverse, you can write U transpose also. Okay, that also work. Anyway, just this is just one information. We will see the questions, and after that it will be more clear. So this is the diagonalization theorem, that let n cross n be the matrix. It is diagonalizable, or or in other words, what we say it in other words, A is similar to diagonal matrix, right? A has n linearly independent eigenvectors. Okay. If it is having n linearly independent eigenvectors, then it is diagonalizable. I have taken this theorem from Berkeley University. Okay. So let's just see these questions. Tell me whether this is true or false. So what they're saying, if you have three different eigenvalues, then This is always diagonalizable. Yes, right? So this is true. Okay, this is true. Let's just see this. If some eigenvalue is repeating, okay, then always not diagonalizable. This is false, right? We have seen this in the earlier module itself, that even if the eigenvalues are repeating, then also the eigenvectors could be linearly independent, right? So it might be diagonalizable. Yes. What if A is symmetric? Okay. Symmetric matrices are always diagonalizable. Let's just see this. If A has three linearly independent eigenvectors, then A is diagonalizable. Obviously, yes, right? This is the definition. Let's just see this. If A is diagonalizable, then AQ is also diagonalizable. See, A is P. Diagonalizable means some diagonal matrix D and P inverse. Can you calculate A square? It will be, interestingly, it will be PDP inverse into PDP inverse. P into P inverse will be just identity matrix. So it is P into D square P inverse, right? So A square is coming like this. What is D square? D square will also be diagonal matrix, right? If D is, let's suppose, 1, 2, 3, then D square will be just a square of this, right? I mean, diagonal elements will get a square. So D square is also diagonal matrix. So A square is also similar to some diagonal matrix. Similarly, A cube will also be, you can easily calculate, will be like this. And that is why actually we need the diagonalization. Basically, diagonalization help us to find out the powers easily. Okay. If A is a diagonal, I mean, similar to some diagonal matrix, then A power n is nothing but P D power n P inverse. Okay. You can just verify this. That's very easy to verify, right? And D power n, it is also diagonal matrix, which means, for example, let's suppose this is some diagonal matrix. Okay. And if I find a square of this, let's suppose, right? Let's suppose this is D. Then what will the D square? If you do the D square, which means multiply this by itself, then it will be very easy. Okay. D square will be this. What will be D power Q? It will be power 3. Similarly, what is D power N? D power N will be power N, power N, power N. Okay. So tell me, is this a diagonal matrix? Yes, right? So D power N is also the diagonal matrix. Okay. So if A is diagonalizable, then A cube is also similar to diagonal matrix. And what is it is similar to? It is similar to D cube. Tell me. This is not related to diagonalization anything. This is easy question. If you have non-zero eigenvalues, all the eigenvalues are non-zero, then A is invertible. What do you think? This is yes, right? Yes, because all the eigenvalues are non-zero. Understood? If A is diagonalizable, then A is invertible. Uh, Diagonalizable means what? Similar to diagonal matrix. So, is this diagonalizable, by the way? Is this diagonalizable? Is this similar to diagonal matrix? Isn't it? Isn't it? Isn't it similar to itself? Every matrix is similar to itself, right? So this matrix is similar to itself. It means, and this is a diagonal matrix. Definitely, it is a diagonal matrix. So it is diagonalizable, by the way, right? Tell me, is this invertible also? Or maybe if you don't want to take this extreme case, you just take like this, right? Is this diagonalizable? Yes, right? It is a diagonal matrix. This is a diagonal matrix. This is definitely diagonalizable, right? Is this invertible? Diagonal matrices are similar to itself. So that's why by definition, diagonal matrices are always diagonalizable. Okay? तुम्हें कुछ करना नहीं है उसके लिए. Is this invertible? Obviously no, because one of the eigenvalue is 0. Obviously no. So I think for this I can say that it is false. If it is invertible, then it is diagonalizable. Um, any example? Invertible and it is need not to be diagonalizable, something like that. So actually, this is also false. Let me just tell you the example. For example, this is the matrix. Okay. This A is invertible, but eigenvectors of A are actually not linearly independent. Okay. It is invertible, but eigenvectors of A are not linearly independent. Or because eigenvalues are same, okay, eigenvalues are repeating. And if you check the eigenvectors, they are not linearly independent actually. So actually, there is no relationship between diagonalization and invertible. So both are false. Okay, both are false. Actually, there is no relation between diagonalizable and invertible. Okay. Okay. Now they're saying diagonalize the following matrix if possible. So how you will be, proceeding with this? You will be finding the eigenvalues, right? You will be finding the eigenvalues. You will be finding the eigenvectors, and then you will be doing it. So, for example, in the eigenspace corresponding. I mean, you can do this, right? You will be finding the eigenvalues and eigenvectors, and then you will be doing this kind of questions. Okay. So let's just do one thing. There are few questions, right? I mean, this is one question. This is one other another question. This is another question. There are few questions that I have listed out. Let's just solve all of these questions tomorrow. And before you come tomorrow, you just try to solve all of these. Okay. And the solution is on the next page. So just consider all of these questions as an homework, right? I think there are 5 6 questions, or maybe more than 6 7 questions. Approximately 10 questions I might be having here. Okay, so consider all of these questions as an homework. Easy questions they are, not very tough question. And let's just discuss all of these questions tomorrow. And then tomorrow we will be starting a very interesting topic, which is singular value decomposition. Okay, so it is easy only. For gate DA should not be too rigorous. Okay, so we will be touching SVD basics and SVD concepts in very very good detail. And once SVD is complete, then we will be starting some little more interesting topic, which is PCA. Okay, do anyone know a full form of PCA? It is principal component analysis. Okay, both are almost similar with a subtle difference. So we will see that. But before we start SVD and PCA, let's just make sure that everything till now is understood by you. So my plan is that tomorrow, tomorrow we will be starting SVD, and obviously I think 2 lectures it will be taking. Okay, to finish SVD and its questions. So after that, maybe if you people say maybe we can start PCA later, we can start projection metrics and these things, and we can finish, okay, all of this. Apart from PCA is actually in the gate DA syllabus. It is not listed as a part of linear algebra. It is listed as a part of machine learning. But it is, I mean, inside the linear algebra itself. I mean, some people teach it inside the linear algebra itself. So maybe we can do the PCA here, or maybe we can do the PCA in machine learning. It doesn't really matter. My plan was that we can do the PCA in machine in the linear algebra itself. Okay, we can complete this PCA in the linear algebra itself, because it is more closely related to SVD, and that is why we can complete both of these topics. Okay, cool. So let's just do one thing. After 2 3 lectures, we will be putting one more quiz. So today's, I think, yeah, Friday, Saturday, Sunday. Okay. By Monday, okay, I will try to put one more quiz by Monday and one more quiz on the Wednesday. Okay. So on Monday, we will put one more quiz, and on Wednesday, as usual, we will be putting one more quiz. So basically, we will be putting two quizzes so that all the concepts you cover, so that, I mean, you get to practice using the quiz. Because if there is a quiz, then you will be having a milestone that, okay, ye complete karke hi quiz dena, right? And once all of this quizzes are over, and these, linear algebra gate DA syllabus topics are over, then we can start this PCA inside the linear algebra itself. Okay, we will decide. But before that, solve all the homework questions which are given. And tomorrow we will be starting a very interesting topic, which is singular value decomposition. Okay. The videos automatically get uploaded. So basically, after 1 and 2 hours, automatically get uploaded. I don't have any control on this. It is by system. Notes I will upload immediately. Okay. Notes I will upload immediately. Okay. So that you can, if you want, you can try. Hers is asking any updates on test series for DA and CSE. CSE will be, I think, in 2 days. CSE will be released. DA we are planning from 25th of this month. Okay. CSE will be released in 1 or 2 days. In 2 days, I think, at most. Okay. DA we are planning by the 25th of this month. Okay. Thank you, everyone. Just try all of these homework questions and let me know. Okay. Let me know tomorrow. Yeah. Okay. Thank you.